So this was the problem that we just discussed, right? Back tension required to cause slip in rolling. I am just reminding you of the equations, right? This is the entry zone back pressure, and this is the exit zone back pressure, and this is the location of the neutral point, right? So these equations you know, and the theory was that when back tension becomes equal to the roll pressure, then the whole contact area has become your entry zone, and the neutral point has shifted from the center to the exit zone, right? So please, if you really want to understand this, then go into the chapter in the book, right? I have summarized it. I do not want to go into more detail of this, but I can ask you sometimes that did you really understand what it was? So in the book, they have explained step by step. So please go to the book. Here we have summarized some equations, but there may be some missing steps which are there in the book. So if you really want to understand this, then go and check with the book, please. Now we come to the actual calculation side. That was sort of a basic background of forces and pressures in rolling, and some basic mathematics and so on. Now from there, without showing you the derivational steps, I will give you the major equations that are practically used in doing calculations if we are really doing the rolling process. As I told you earlier, compared to forging was a straight line process, isn't it? When we were doing upsetting and so on. Here there is a roll, and as the material comes in contact with the roll, the angle keeps on changing. So there is a tangent, right, with the roll surface and the slab, and therefore because of the angle, the mathematics is slightly more involved, but that is okay. I am not interested in doing the derivations. If we were interested, you would easily understand it. It is not an issue. But we have to cover a lot of topics and many manufacturing processes. So I am directly giving you the equations now. Roll force or roll separating force, whatever you go, for low friction. We are saying for low friction because these are the set of equations for high friction. Just like in forging, remember that if the friction was low, then barreling was not happening. But if the friction was high, then barreling was an important issue, and you were changing from sliding friction to sticking friction. So here also, therefore, for low friction, as long as friction is low, the roll force is L W y bar dash, right? L is the length of contact, not length of the roll, length of contact, and W is the width, remember. Y bar is the average flow stress, and dash is because of plane strain. Torque per roll, you simply know that force into force arm is torque and moment and so on. So torque is F L upon 2. The force is there, force, and L upon 2, half distance. So simply this is the torque. The length of contact, this length of contact, how do you find it? L is equal to under root R delta H. Capital R is the roll radius, and delta H is the change in height or thickness that happens during the rolling process. If originally it was H naught, if finally it is HF, then H naught minus HF is the delta H. So you find the length of contact from here, then you substitute it there. The other thing, because W is the width of the slab piece, whatever you have, a stock material, and this is the material property, Y bar, right? So these are the equations if the friction is reasonably low. If the roll friction is high, then you have this, but you multiply it by a factor, LW y bar dash 1 plus mu L upon 2 H average. Mu is the coefficient of friction, L is still the length of contact, and this is H average now, not delta H. If it was H naught in the beginning and HF in the end, then this is H naught plus HF by 2, the average. If you want to find the power required per roll, then you know that this is an old equation of mechanics. Power is torque into, this is omega, this is the angular velocity, this is not W. This W was the width of the piece. This is a small omega, which is the angular velocity, right? Number of angles per unit time. So this is the power required per roll. From here, if you want to convert it to metric unit, directly to metric unit in kilowatts, then you are converting the angular velocity to RPM, capital N. It is pi f L n upon 60,000, directly in kilowatts. Directly this value will be in kilowatts now. F is the roll force, which you have found from here or here, whether it is low friction or high friction. You have found the roll force, so F is there. L is the length of contact, and if the RPM of the roll is known, then power per roll, this is power for one roll. So if there is a set of two rolls, then the total power of course will be more, right? So these are the equations. So once you have this set of equations, let us now apply to an actual manufacturing force calculation and so on, the power required in rolling, right? Not a theoretical one, an actual one. So let us read it together and then we will see. A 22.86 centimeter wide, so W is given, 6061O aluminum strip. So this is the material. It is an aluminum alloy, 6061O. Is rolled from a thickness of 2.54 centimeter to 2.03 centimeter. So this is H naught, this is HF, isn't it? For a roll radius of 30.48, capital R, and a roll RPM of 100, capital N, estimate the total power required for this operation, right? So again, take down the data, note down all the knowns and unknowns, write them down. Then you can go back to the previous equation, okay, and then you try to solve it. And pause my lecture, do not listen further unless you are very sure that your solution is correct, okay? So please, if you are starting to listen to me again, then it means that you have already solved it. So okay, so if you are listening to me now, you have already solved it. Now we know that in all of these calculations, the flow stress of the material is required, Y or YF or Y bar, whatever, right, in the equation. Now in the power equation, there is Y bar dash, right? Now this material is given, So again, you will have to go to chapter 2 of the book. We have used that table earlier in forging and so on, so that you can find the value sigma is equal to K epsilon N. Remember, sigma is equal to K epsilon N. We had an earlier page where we showed you this stress equation in the plastic region, and from there we had given you the equation for Y bar, also the average. This sigma or Y, right, K epsilon N is the normal flow stress, but Y bar, the average one, the equation is also given. So you can find the Y bar. In that Y bar, there will be capital K and a small n, two material parameters. So from the table, 6061O aluminum, if in the table you find this material, then for that material, the value of capital A and capital N will be known. So from there, you can find the Y bar. And if it is Y bar dash, then it is just that factor of 2 by root 3 and so on, which is there in the condition that plane strain is applied, isn't it? So from the table you find the K and N. Once you have that, then from the Y bar equation you find the Y bar, and from the multiplication factor you find the Y bar prime, which is for plane strain. Once you have it, then you just substitute the values in the equation, taking care that all you are in a similar unit system. Here on this page, I have compiled for you all the equations from rolling. It took me quite a long time typing and so on, but every equation about rolling that is there in the book, in this chapter, roll pressure, in the entry zone with back tension, roll pressure in the exit zone with front tension, the parameter H in these equations, roll force in an integral format, and the approximate, this is the exact one, the approximate roll force. If you use this factor, then it is for high friction. If you assume no effect of friction, then you remove this factor. So for low friction, it is this. So it is both equations given together. If you take only this first part, then it is roll force with low friction. And if you take the whole equation, it is roll force with friction. Then roll torque, right? The roll contact length, approximately, the power per roll in the kilowatt units and in the horsepower units. So all the equations are there, and in these equations, once you want to find out the flow rate and y bar and so on, so I am reminding you that y bar is k epsilon n upon n plus 1, and y bar dash, right, the plane strain version, you just multiply whatever you have by 2 by root 3 or 1.155, right? So whether you have to use yf or whether you have to use y bar, if you have to use the dash, the plane strain version, then just multiply that yf or that y bar by 2 upon root 3 or 1.155. So all the equations are here, and for your problem, if you have to find the power, in kilowatt, then this is the equation that you use. The RPM is given, but the length of contact and the roll force are not given. Length of contact, you go to this equation. Here the roll radius is given and the H naught, HF both are given. So delta H is then known. So now L is also known. For roll force, you use this equation, and because friction was not given as a factor, so you use only this. Then for y bar, you use this equation, and in this equation for epsilon, remember epsilon is ln h naught by h1. So if you have to find power in kilowatt unit, then this is the formula, right, where F is LW y bar dash, where L is root R delta H. So just substitute R, the roll radius, delta H, the initial height minus the final height. So this L is in centimeters now. W was given as this much in centimeters. From table 2.3 in the book, 6061O aluminum, and please, I implore you, please go to chapter 2, find table 2.3, and if you like very much, take a copy of table 2.3 and keep it with you. You can always make a scan and save it anywhere you like, because this will be used throughout the chapter in forging and rolling and extrusion and wherever, because we want to find this K and N. So for 6061O aluminum, go to the table, don't take the value that they are showing, confirm that this is right. And once you have that, and then this is there. Now in the equation, you first have to find epsilon. Remember, epsilon is ln h naught upon hf, because y bar is equal to k epsilon n, right? Epsilon. So therefore epsilon, you know, is ln h naught upon hf. So you put the values of h naught and hf, you find the value of epsilon, and then you find the y bar.